Hello and welcome to Module 14, Lesson 3, which is intrusive activity. So when we talk about intrusion or intrusive activity, we're talking about things that are under the ground. So we have to talk about igneous rocks because they form from magma under the ground. And so just to review, we have a bunch of different types of igneous rocks. So remember, extrusive means that it forms on the surface of the earth and there were no crystals, so you couldn't see different colors. Whereas if it was intrusive, there were different colors like granite in this picture, diorite, granite, pegmatite. Those are all intrusive rocks because we can see different minerals. All right, so if we look at volcanism on the earth, volcanism happens because magma is coming to the surface and coming out. And so that's what we mean by volcanism. And then magma underground, if we're talking about intrusions, magma seeps in, fills in cracks and things as it moves through under the surface. And so you can see here, this right here is magma that has forced its way through a crack in a rock. And that's called an intrusion. All right, so big intrusions are plutons. And plutons are basically formed underground, so they're intrusive igneous bodies. And they are generally because of two ocean plates colliding. And so you get large, huge rocks. And so in this picture, you can see there's a pluton. And then this pluton's been lifted because of uplift and plates moving around, and then it's been eroded, and then plants have grown on it. So, so that's how they get to the surface. So this was formed underground. And if we were to look at it closely, we could see different minerals, so we know that it was formed underground. All right, and then sometimes we have big plutons, and big plutons are called batholiths. And so basically they're huge mountain ranges when they become exposed on the surface. So here's a picture of Yosemite Valley, and there's the iconic Half Dome right here. And so these are huge batholiths. The whole Sierra mountain range is all a batholith. So it was all formed underground, magma hardened. Nothing about these mountains were ever volcanic. They never erupted out of the surface. They just formed underground. And then now they're exposed because of California uplifting, and now it's eroding away. And it's been eroded by glaciers. So remember the U-shaped valley. So a U-shaped valley indicates that that was formed by a glacier, whereas a V-shaped valley was by a river.
Most of the national parks in the United States were founded on their geology. Yellowstone displays volcanic features. The Grand Canyon shows millions of years of sedimentary history. And here in Yosemite, the geologic story is primarily one of granite. Granite is what's known as an igneous rock, which means it's born of fire. It cooled and solidified from magma or molten rock, and when magma erupts on the surface, we think of it as lava. Basically, granite started off as something similar to that. It was red hot, fluid rock, but instead of making it up to the surface and erupting as lava in a volcano, it stayed many miles below the surface and cooled there very slowly over thousands of years. And because it cooled so slowly, it allowed very large crystals to form.
It's a very coarse-grained rock, and that's the key to its strength. This rock spent a long time at high temperatures, cooled very slowly, and that allowed a lot of the cracks to be annealed out of it, making a very strong rock. So the glaciers had a hard time moving it, and that's what allows you to carve the kind of landscape that you can see over my shoulder here.
Granite is among the toughest rocks on the planet. I mean, it's very, very strong stuff. So when glaciers were moving through here, they certainly were able to erode and sculpt the landscape some. But a lot of the domes, the smooth ridges that we see up here in the high country, they're really a testament to the fact that glaciers weren't able to do a lot of eroding of this landscape.
One of the things that makes Yosemite such a great place for us as geologists to work is that nature has taken these rocks and polished them for us. And so we can come out here and literally crawl around on our hands and knees looking at beautifully polished specimens that in places are polished almost as well as a commercial company would polish up your kitchen countertops for you. So we can see the relationships among these minerals. We can see into the guts of what was a magma chamber and see what was going on then, frozen in time for us.
Every visitor to Yosemite, I think, experiences granite in some way. I mean, you can't hardly not experience granite in a park like this where most of what you see is granite. And that can range from just taking a quick stroll off the side of the road to a place like Olmsted Point, to taking the hike up Half Dome, up to the summit, to spending 4 or 5 days climbing up El Capitan. I think more than most visitors, rock climbers have a really good sense for granite.
Climbers take advantage of lots of the geologic features of the granite, such as these feldspar knobs that stick out, such as the occasional cracks, such as some of the dark blobs of different kind of rock in the granite that weather out that you can use for handholds or footholds. Okay, so what minerals have you got so far?
Biotite, quartz, and potassium feldspar.
Okay. What else might you expect to be on this rock? Well, I got my class, it's a first-year seminar at the University of North Carolina. We come out here every fall, and we always bring them into Yosemite for at least a day because it's an experience that everyone needs to have as soon as possible in their lives.
You know, Yosemite is a great place to just come learn more about granitic rocks. You'll see them everywhere. You can easily walk around on them, look at them closely. And I think it helps that you can be studying these rocks in such an inspiring place, you know, where the landscape just sort of opens your mind up to trying to understand it better.
When I walk around here and look at the granites, I think I understand a lot about how most of the features that I see formed. I can see cracks that filled with magma. I can see blobs of a dark magma that were caught up in a lighter magma. Then we can understand that by studying it, by doing chemical analyses, by doing experiments to try to duplicate some of these things. But there are a lot of features out here that none of us understand. When you walk around on these glaciated surfaces, you can find a lot of really unusual things. Some of them I think we understand, and some of them are great mysteries. I've been to this place maybe half a dozen times, and I really have no idea how this formed. It's one of the weirdest things I've ever seen in a granite. Seeing things like this is kind of humbling. I think we understand a lot about the granites in Yosemite and how they form and over what time periods they form and so forth, but you walk around a corner, you run into something like this, and it's really humbling. It says there are a lot of mysteries out there still left to solve.
I think a lot of visitors, when they come to the park, they're not thinking about geology per se, but you know, they're here to experience this beautiful place. It's right here in the core of Yosemite that we have the best exposure of granite, and that's also where we have the most amazing landscapes in Tuolumne Meadows, in Yosemite Valley. They are a direct result of the granite that's here.
Right, so learned a lot about Yosemite. So stalks are just smaller. So you can see here's a big batholith like the Sierra Nevadas. And then here's a stalk. So a stalk would just be a small kind of irregular shape that is pushed up through other layers. And then a laccolith, what a laccolith is a layer that is pooled up kind of between other layers. So you can see this would be our stock, and then we've got this laccolith that kind of builds on top. And so sometimes you get mounded mountains, kind of like what you see here in the picture. All right, and then we have sills. So a sill, the way I remember it is it's a windowsill. So a windowsill is flat, horizontal. And so here's our sill. So you can see this is obviously a very different rock that is formed in here. And so these are igneous rocks. So they're not layers of sediment like the Grand Canyon, but this is an actual pool of magma that seeped in through the layers and formed. All right, and then dikes. Dikes move through different layers. So you can see the stock is bigger, and then this is just moving up through these different layers, whereas a sill is horizontal. So a dike is perpendicular or at least tilted slightly, and then a sill is flat. And that's the biggest difference. All right, and then textures. So remember, coarse grain textures were when we have rocks forming underground, and fine grain, which is where you can't see the different minerals, that forms above ground. So if we're talking about intrusions and we're talking about underground, then all of these are going to have coarse texture because they formed underground. All right, so here's just looking at these things again. So just be familiar with them. Batholith, which is also Pluton. It's just a large Pluton. And then we've got our sills, which are flat. We've got dikes going through, traversing through layers. Then we've got a laccolith, which is a big pool. So it's kind of like a sill, but a very large pool. And then we've got, if it comes above the surface, then it's no longer an intrusive body. It's just a volcano instead. All right, so we see a lot of this activity where we have plates colliding. So in California, we have all of these things. And the reason for that is because we have an ocean plate and a continental plate colliding. And so that's when we see all of these features in California. And that's because we are on that plate boundary.
I'm JB Waterman. It's time to wake up and live. Okay, what if mountains could talk? What would they say if I asked them, where do you come from? Where do you come from? Where's home? So I asked this question to one of my favorite pieces of the California landscape. The Sierra Nevada Mountains! The Sierras are a beautiful, rugged granite mountain range in California that stretch for 350 miles. They contain Yosemite National Park, Kings Canyon National Park, Sequoia National Park. They're where John Muir roamed. They are home to the highest peak in the lower 48 states and the largest trees in the world. They are awesome. But why does it exist? What made it? I couldn't just ask the mountains these questions. I had to ask an expert who speaks the mountains' languages. Enter Greg Daring, geologist and mountain communicator. I asked Greg a simple question.
What made the Sierra Nevada mountains?
And I got a lot of big words and complex geology.
There's a lot of heterogeneity. The Farallon plate density contrast is called subduction. Different batches of magma. Asthenosphere, and at the base of the lithosphere, called a batholith.
Now I cut past all that scientific talk, and guess what? There is still a lot of mystery around how the Sierras were made.
We know how the Sierras, we know how the rock that constitutes the Sierras formed. There's a lot we don't know regarding the uplift of the Sierras.
Sierra, 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 Sierra.
So one thing scientists totally understand is how the granite that makes up the Sierras was formed. So back when dinosaurs roamed California, there was a chain of volcanoes standing where the Sierras are today. Now one plate was going underneath another, causing a bunch of bubbling up of molten rock. Underneath these volcanoes, in their bubbling basement, is where the granite of the Sierras was made.
This never erupted from a volcano or anything like that. What we see here, this always lay beneath a volcano, essentially in the plumbing system of that volcano.
So, walking along the hard rock of the Sierra is actually walking along the core of ancient volcanoes. Literally. The rock that makes up the beautiful peaks of the Sierra indeed started out miles and miles below the surface underneath ancient volcanoes. And to a geologist, this is like buried treasure.
It's totally buried treasure. Yeah, I mean, who hasn't wondered, kind of what was underneath when you see something cool like a mountain range. The Sierras are a mountain range and simultaneously are showing us what's underneath other mountain ranges, like the Andes or like the Cascade Arc.
Now comes the mysterious part. How did granite go from being miles below the surface to 14,000 feet above the surface?
So, I mean, that's a great question. We have not settled with a single consensus on what did drive and what continues to drive the uplift of the Sierras.
How did your rocks form? Why did you get so high?
Some scientists believe that the Sierran granite was pushed up from below, but Greg says that we shouldn't think of the mountains necessarily as being driven up at all.
We don't know that the rock that makes up the Sierras was necessarily pushed up, because it, maybe more than being pushed up, which does happen with some mountain belts, like say the Himalayas, whereas in the case of the Sierra Nevada and Western North America, rather than a collision that's pushing up mountains, we may actually have built mountains by the addition of this hot, buoyant material from below up into the crust.
When the plates stopped going underneath one another, the volcanoes above the granite dried up and they gradually eroded down to nothing, while the granite itself floated slowly towards the surface and was exposed and gradually eroded into sharp peaks. Pretty cool, huh?
Sierra, you're a mystery, I know.
Some geostuds at Caltech believe that there's an ancient root of the mountain made of incredibly heavy material that has been holding the mountains down. And this root is tied to why they're so high.
Their idea is that the mountains are so much higher in the south because that dense keel has separated, and they use the term delaminated, from the base of the batholith, thereby sort of pulling off, there's no longer a heavy, dense anchor that holds the batholith down in the southern Sierra, allowing it to float higher? Exactly.
These are the questions, Sierra, Sierra.
And Greg says there's also evidence that the Sierras look so high because the land to the east has literally collapsed. While those ancient volcanoes were dying, the area of Nevada and Utah were being stretched thin by plate movement. Now, as Nevada got thinner, its land dropped away along the eastern edge of the Sierras, making the sharp, dramatic eastern face of the mountains that you see so clearly from Highway 395. So while the beauty of the Sierras is evident, the reasons behind their height are still shrouded in a fair amount of mystery. And as geologists work to translate the language of the mountains, they also have to work to translate the many languages that exist within the field of geology itself.
There's no single language that, geoscientists speak. A person who's taking modern day GPS measurements may speak to a hydrologist who's an expert in river systems and the development of canyons. That person may speak to a seismologist or somebody that studies earthquakes and faulting, and they really don't. They may try to speak the same language, but they don't. People come at these problems from so many different ways, and no one discipline is going to answer the question about how the mountains formed, right?
Do you think there's a Nobel Prize waiting for someone who answers the question?
There's no Nobel Prize in geology, unfortunately. There should be.
So I hope that you will talk to me when I ask you the questions. Where did you come from, Sierra, Sierra? Sierra.
All right, so plutons, if we're looking at plutons, we've got that coming off of a batholith. And so they're basically formed by that ocean crust colliding. And so here's all of our different terms. So just make sure you guys know these. Sills are in between. Plutons are a large magma body. Batholith is even larger. And a laccolith is kind of a dome shape in between the layers, whereas a sill is more flat. And that's it.